Now, let us say how do we measure a distal object, or we have talked about the gaseous systems, gas particles having a Maxwell Boltzmann distribution. But let us say when you talk about solids or liquids, then they are not really moving from their own positions, right. So, a solid atoms are fixed in a particular position, they move around that from a center. So, how do we actually measure temperature for that? Will it be kinetic energy for that, or will it be something different? Yeah, some of you know the answer already from chemical principles 1 course, but I am going to repeat that little bit here. So, let us say we want to calculate the temperature of this particular lava. How do you do that? We are not going to measure by a thermometer, because looks like it will be very hot and thermometer will break. So, what is the microscopic basis of temperature in that particular solid, and how do we measure the temperature of the distal object? So, in order to answer these two particular questions, that we have to understand that thermal equilibration in solid also leads to a particular distribution of frequencies of the emitted electromagnetic radiation, which is known as blackbody radiation. So, in this case now, similar to our kinetic theory of gases, we have talked about Maxwell Boltzmann velocity distribution. Here we are going to talk about distributions of frequencies of electromagnetic radiation emitted from the particular object. Now, what do we mean by that? We mean by that when an object, a solid object, is in thermal equilibrium, then the atoms of that object will fluctuate, or rather charges present in that particular object will fluctuate, giving rise to electromagnetic radiation. So, we are going to show a demo of that. A charge, positive charge is kept somewhere, and these are the charge fields associated with the charge. So, when we use a linear when you move the charge with a linear velocity, it does not actually give any electromagnetic radiation. However, when you move it in a sinusoidal manner such that the charge oscillates, it will give rise to an electromagnetic radiation corresponding with the frequency of movement of the particular charge. So, now imagine that in solid objects which is kept at a very high temperature, for example, a very hot iron rod, that atoms in that rod will actually fluctuate and the charges within the atom of the rod will fluctuate, giving rise to electromagnetic radiation. Now, it turns out that just like velocities, that all the particles will not have same velocities, similarly the emitted electromagnetic radiation will not be of same frequency. There will be a range of frequencies in which the radiation will happen, and that is given by a law called Blackbody spectrum. So, and that also surprisingly looks very similar to Maxwell Boltzmann, in the sense that if we plot it, you will see an increasing and then decreasing behavior. So, the nu square here increases with the frequency, and this particular part decreases with the frequency, giving rise to this particular distribution. And as you can see here, that at different temperature it will give different type of blackbody spectrum. Here also the temperature is fixed, the macroscopic variable which is temperature is fixed. However, individual frequencies are not having the same value, just like our gas particles. When you get the analogy with the gas particles of same temperature or the macroscopic value of the temperature having different velocities, similarly the solid object having the same macroscopic value of temperature, giving rise to different frequencies of electromagnetic radiation, and overall those frequencies will shift towards the higher frequency, rather we can say that the peak of the distribution will shift to the higher values as the temperature increases. So, and that is shown here. As you can see that you know that the frequency of red light is less compared to the blue, right. So, as we go from low frequency to the high frequency, you can see that the color changes. So, by looking at the color of an object which is emitting electromagnetic radiation, we can figure out the temperature of that particular object. So, I will show you a demonstration of that here, and this demonstration has been taken from Fate, Colorado, PHET Fate, Colorado. So, this is a typical blackbody spectrum, and in which this region is the visible range. So, as you can see that right now the temperature is around 5000 Kelvin, almost the temperature of the sun, and a major portion of the peak of the distribution falls in the visible range. Therefore, one can see that object. So, if something has higher temperature or emitting radiation in the visible region, then we will be able to see that. For example, when a hot iron rod is emitting radiation, we can see that it is red hot, we call that red hot. Now, it becomes even hotter, then it will become from red to yellow, and finally, if it is super hot, then it will adopt a bluish color. So, however, as the temperature goes down, if I go down the temperature, decrease the temperature, then what happens is that it will shift towards more and more lower frequencies. So, as you can see, I am decreasing the temperature to 3000, and it is shifting to higher wavelength here, which means the lower frequency. And if we go down to as low as the normal human temperature, which is 300 Kelvin, so I am now 1200, I have to go even lower, So, at 300 Kelvin, as you can see that the peak of the distribution is in a micrometer region. So, and that is the region that is associated with IR radiation. So, our body, we are also kind of a black body which is emitting radiation, some electromagnetic radiation, but we are radiating a distributions of frequencies, but all those frequencies are in the range of in the IR region, and therefore, our normal eyes, we cannot detect anything that is beyond our visible spectrum. Therefore, we cannot see the radiation coming out of our body. So, what kind of radiation it is? We call that heat, and heat is nothing but IR. So, we are emitting IR radiation that is perceived by something called heat what is that camera called? So, it is called infrared camera, where or heat sensor camera, which senses the heat, and then one can find out the presence of an object. And also you can see that when you look at that body, you will see that although our temperature, when you measure our temperature of the body, it is one value, right, but when you measure through a heat sensor, you will see a distribution. You will not have the same value, some portions will be like hotter, some portions colder. So, it is like that all the bodies are interacting with each other, however, one gets only the macroscopic sense of the temperature. So, similar principle of using the blackbody radiation has been is used in something called infrared thermometer. So, we have one infrared thermometer here, and we are going to measure temperature through that. So, let us see what is the temperature of this particular water, which is still hot, and that time we measure to be 40 degree. Let us see how much it is. 40.9, if you want to see. Do you want to try? You try it and tell the temperature, and tell us that what is the temperature you are getting.
40.5.
40.5. Try this one.
21.
So, it is almost same as our normal thermometer, however, it is much easier, and one can measure that. So, for example, I can measure your body temperature. It is supposed to be how much? 37 degree. Yes, the head gives 34. This particular infrared thermometer goes works in the lower range up to let us say 100 or something, but we have a better one. We have this one, it is called pyrometer, which again follows similar things called Stefan-Boltzmann law, which actually measures the energy density here, and that works beyond 200 degree centigrade. So, looking at that yellow light, since we know that yellow falls in the range of 1000 something, so we can actually measure the temperature of that. So, let us measure that and see what we get. So, we have to focus that light, and it really does not matter whether there is a veil outside it or not. .1165, it fluctuates around it. Typically, you can say 1104, 1136, something like that. that is it. So, and the temperature of this light, which we saw yesterday, around 300 degree, you can say it fluctuates around that. Okay.
But we cannot feel that high temperature. Such high temperature.
If we touch that, we will of course feel that temperature. This is used to measure the electromagnetic radiation that is coming out of that. So, since we are at a distance, we are not feeling the temperature. However, if you touch the object, you of course will feel the heat.
But that cannot.
Yeah. So, this light, if you let us say if you go to the source of the light, you will have that. This range, the range of this particular one, I know the lower range 200, but I do not know the higher range. I do not know how high it can go though. But the object of the point of, like, you know, when people try to calculate the temperature of the lava, they are not going to really go and measure it, right. So, we can do it from far away, but although we may not feel that, but if you actually touch that source, then we will see that the temperature is high. Okay. So, we have seen that many different ways of measuring temperature, that we can measure the temperature by volume of expansion of gases, solids or liquids, through resistance, through blackbody radiations, and you know all possible ways we can actually measure the temperature of a particular system. But again, the temperature is a quantity then which gives you, when the temperature is at equilibrium, then it gives you a distribution of a particular distributions of gas molecules or frequency of electromagnetic radiation of the solid. So, it will give you a fixed distribution. So, in a microscopic level, things are not going to have one particular value, it will be always having a distribution, and we are going to learn later on that why that is such, why we always have a distribution in a microscopic level rather than one particular value. When you talk about, as I explained to you before, right, when you talk about 1 liter of volume in a macroscopic sense, it does not mean that it will always have 1 liter, it will fluctuate around that, and that fluctuation is due to the motions of molecules that are there in that glass. All those, and you will see that all the macroscopic variables like temperature, pressure and volume that you are going to measure later on, they are nothing but averages of all those measurements. They are not fixed values, they are just average values. And in the same way, the Maxwell-Boltzmann distribution is giving you an average effect as temperature as one value, although it has many possible temperatures for individual molecules. Now, if you go and individual molecules and let us say what is the temperature of that molecule, you calculate the kinetic energy of that molecule and that will be the corresponding temperature. So, that is why it is interesting that when you take out that high energy molecules, what will happen? What do you think will happen, that from let us say given n molecules which is having Maxwell-Boltzmann distribution, you take out the molecules which are having the higher velocities, that means from the tail you take out some. What is going to happen? What do you think is going to happen? So, what is going to happen is that when you take out that, so you are reducing the overall energy of the system. So, now it is going to redistribute it, the velocities are going to be redistributed again, having a different temperature, and the distribution will shift to the left. And same is true for if you take out the cold atoms, cold molecules, and then it will distribution will shift to the right.